Okay, is this okay? Everyone hear me? Great. So I'm going to present some work that I've been doing for the last 3 years or so as part of the AMCG group in Imperial College. So I'm working on the fluidity ICOM model, and everything I'm presenting here is based on that model. Just a quick thank you to the co-authors, most of whom are organisers for this session as well. I wonder why I got a talk slot. Quick outline for the talk. I've only got half an hour or so I might not get through all of this, but I'm going to spend a little bit of time on the motivation for this because I think this is quite an important problem, and it's one of the problems where I think using multiscale and adaptive methods could really give us something. Luckily, Matt described fluidity in the first day, so I've got one slide also on fluidity, so I don't need to really introduce fluidity anymore. I'm going to talk a little bit about some of the verification studies we've done with the ecosystem. If I have time, I'll do the restratification problem, but I may not get there. And then I've got a couple of slides at the end with some very vague conclusions. So what I'm going to talk about are critters, or plankton. So we have phytoplankton, so here's some diatoms, and the things that eat the phytoplankton, the zooplankton, okay? And the reason why these are interesting is that you get plankton blooms. So this is one in the Bay of Biscay, that's France. And these are quite difficult simulator things to simulate in a model because you can see the really fine structure that goes on in there. So if you're doing a global simulation, the resolution you need to capture all the dynamics that are going on in there is actually really, really high. Okay, so currently it's now impossible to get the kind of resolution to capture all these dynamics while doing a global simulation. So this is kind of perfect for multiscale, and moreover for adaptivity because you don't know when or where these things are going to occur. So, and the reason why this is important globally is that we don't currently estimate the biological productivity using numerical models very well at all. We're orders of magnitude kind of out. The reason being is that you can see that most of the productivity is in the coastal oceans. The scale here is logarithmic. So red is like 10 times bigger than orange, which is 10 times bigger than green. So everything is in the coastal region. But you get these large areas where basically nothing much happens, except occasionally you'll get a plankton bloom. Because of the size of this area, these blooms can be large, and they therefore give you a large contribution to the global carbon and nitrogen cycles. So they are quite important, but quite difficult to study because by the time you get a ship out there, it's gone. So the only real recourse we have to do this is via numerical modeling. I'm going to talk a lot about nutrient fluxes and things like this, so I thought for the people who know nothing about ocean dynamics and ecosystems, I put this slide in. Basically, you have your phytoplankton sitting happily in the ocean column. They need sunlight because they photosynthesize, but they also need nutrients. So the sunlight comes from the surface downwards. The nutrients tend to come from depth upwards. So phytoplankton like to sit in this nice little region where there's enough nutrients to grow and enough sunlight for them to use. So if you could get nutrients close to the surface, you can get a plankton bloom because you've got higher amounts of sunlight and higher amounts of nutrients. The way you can do that is you can either advect your nutrients. So for example, something like Ekman pumping, where you have an eddy and you can draw nutrients up, or you can move what's called the upper mix layer up and down, oscillate it around. The upper mix layer is effectively everything above this line is mixed and constant. Everything below it is stratified. If you move this down, you move it into the nutrient sink, and then you mix everything up to the surface. So there are basically two ways to get nutrients to the surface to cause a plankton bloom: move the upper mix layer up and down, or advect nutrients to the surface. Okay, and as I've already discussed, this is kind of crucial because we currently in global simulations don't really get the productivity in the oceans correct. So, and one of the reasons we think that this is occurring is that we're not simulating the sub-mesoscale, the really kind of order kilometer, 10 kilometer scale processes in our global simulation in the areas where these plankton blooms occur and are large enough to affect this global budget. So lots of people have done lots of work. I'm going to concentrate mainly on one author, Marianne Levy, who's done a lot of work on this, where she has looked at the effect of increasing your model resolution on how much biology you get out of the model. So ignore this line, but to pay attention to the dotted line and the thicker black line. That's a low resolution model, that's a high resolution model, and as you increase resolution in your model, you get more productivity. Makes sense? And if you look above, this is the low resolution result, the high resolution result, you can see you get tighter curls of the vortices and the eddies and everything else. Pay attention to the vertical velocity scale, it's about double. So you get minus 40 meters per day to 40 meters per day on the high resolution, and about minus 15 to 15 on the low resolution. So increasing resolution, you start to resolve these sub-mesoscale processes, and lo and behold, more productivity at the surface. Perfect, you would think. Except she did another study on a bigger domain, different domain, and she got exactly the opposite result. So here, sorry, these have been reversed in that this is now the high resolution one, this is the low resolution one, and you can see the high resolution is mostly white, i.e. nothing much is happening. So if you look over long time scales on this larger domain, you get the opposite result. If you go high resolution, you actually get lower productivity in the ocean. So that's basically the fluxes of nutrients to the top. What about moving the mixed layer depth? So again, Marianne Levy, back to the first one where she did the, the channel with the low and high resolution. And here she added a wind to the surface as well. Excuse me. So in the case with no wind, you can see there's very low productivity. And when you add a randomly fluctuating wind stress on the top, the upper mixed layer moves up and down, flux of nutrients to the top, and lo and behold, you get increased productivity. Perfect. Except a master's student of mine last year found exactly the opposite result. So here, he looked, Nick Lutzko looked at increasing the forcing frequency of the data. So he had 10-minute data and 6-hour data, as well as 3 and 1 hour data. And as you decrease the forcing frequency, i.e. you go to less gustiness, less mixed layer depth moving up and down, you actually get lower productivity at the surface. So all in all, a very confusing picture, depending on both your temporal scales and your spatial scales when you're modeling this. So this is a non-linear problem in a non-linear ocean with non-linear processes going on, and then we're going to try and add adaptivity onto this, which is another non-linear process on top. So this is why my conclusions are very vague, because this is very complicated stuff. So I'm going to use fluidity. What Matt didn't put on Monday is a snazzy new logo, which I spent all of 10 minutes designing, so I thought I would show you this. For those of you who have short memories or weren't here on the first day, fluidity is an open source finite element model that uses unstructured meshes, has multiple discretization, CD, DG, control volume. Parallel, we can scale to tens of thousands of processes. We use HR adaptivity, and we also have a nice user-friendly interface. And the reason I mentioned Python is that although fluidity is mainly written in Fortran with bits of C and C++, the biology model is all written in Python, so it was super quick to put together, although it was very difficult to actually get right. But to actually develop it in the first place was like a day's work. When I started, fluidity would not be able to do anything like what the problems is that I'm trying to simulate. So first thing I had to do was add surface fluxes, sunlight and wind stress and everything else. This is an old slide because we still say icon. I should say fluidity now. So when I say icon, it's fluidity. Just sort them around in your head. So bulk formulae take things like wind speed, temperature, air pressure, dew point temperature, and variables from your model. You'll see surface temperature and surface currents, and then give you back to your model momentum fluxes, salinity fluxes, and heat fluxes. This basically forces the surface of the ocean and does interesting things. Also needed to add a turbulence model, because otherwise we can't simulate the mixing layer. Even with adaptivity, we can't get down to the subgrid scale turbulence in an ocean. That would just be impossible, so we still need parameterizations. So this is a 2-equation turbulence model, GLS, generic length scale. It has an equation that is for the kinetic energy. It's just advection diffusion with some extra source terms and sinks on the end. And you get this generic term, psi, again, advection diffusion with some source and sink terms on the end. So 2 quite simple equations to solve just with some source and sink which add energy or take away energy. And the cool thing about the GLS is that this psi term can be cast in terms of K and L and this constant with P, M, and N as exponents. If you choose those correctly, then you can back out more standard turbulence parameterization. So for example, if you set p to 0, m to 1, and n to 1, you end up with psi equaling kl, which gives you a kl turbulence model, which is kind of Melo-Yamada type model. And you can also set p to these values, and you get a k-epsilon model. Okay, so all the results I'm going to present are using the k-epsilon model for no reason other than that that's a popular one. It seems to work. I have tried all of these. They do work as well. And obviously we need a biology model. So we're using a really simple biology model. We only have 6 states in total, not one of these that have 20 or 50 states, because this is hard enough, thank you very much. So we have phytoplankton, zooplankton, detritus, and nutrients, which are split into ammonium and nitrite. So phytoplankton.
We can associate with sloppy feeding though.
Sloppy feeding, yes. So phytoplankton needs sunlight and nutrients. They get eaten by zooplankton, but zooplankton aren't perfect at eating. The phytoplankton, they die and they have sloppy eating. That all forms detritus, which then remineralizes back into nutrients, but some of it sinks down to the bottom. And all these fluxes are nonlinear, and moreover, most of them have discontinuities in places as well. So this is actually quite a difficult problem in terms of adaptivity. And the last thing is adaptivity. Matt went over all of the adaptive routines on the first day. But basically we use the Hessian. So we work out the curls of various fields, and we can add these fields together. So it's very flexible in that I could choose one field, or I could choose 10 fields on which to construct my metric, which we use to define what the mesh is. So here, for example, I've adapted to the kinetic energy in the turbulence parameterization. And you can see I've got a nice fine mesh at the surface, because there's a sharp gradient, because there's nothing above it. I've got a nice fine mesh at the bottom of the mixed layer, and it's reasonably coarse in between. And this goes down 1,000 meters, and it's very coarse at the bottom. And this is the domain I'm going to be using for the majority of the rest of the talk. It's a pseudo 1D column, so it's 100 meters across, 100 meters back that way, and 1,000 meters down to depth. The reason being that I don't want to overcomplicate things yet with horizontal advection and everything else. Just want to concentrate on the vertical. So does it work? Yep, it's good. So we recently published this in Ocean Modeling. We compared to another turbulence model, Gotham, and you can see that the dots are data, and the fluidity, both adaptive and fixed mesh, goes through the dots, as does Gotham, so everything looks okay. And if you look at the temperature, then if you can spot any differences between those two, you've got very good eyes. This is the Gotham temperature, a little bit warmer, and this is the observed temperature. So all looks pretty good and works with the traces and the turbulence parameterization. Is it worth it? Yeah, it's not too bad. Given we're only in a 1D column, 1 meter fixed mesh would have 4,000 elements, and I can do the same simulation just about with 200 elements. So I'm talking an order of magnitude fewer elements in the simulation, which is just for a 1D column. If you then extrapolate across that to the ocean, then we should be saving 2 orders of magnitude type elements, the number of elements. So it should well be worth it. Okay, now comes the tricky part, adding the ecosystem. So there are 3 ocean stations that we've considered in these 1D columns. One is Station Papa. This is the one that everyone simulates if you're doing turbulence parameterization of the ocean. The reason being there's very little horizontal advection in this area. So your turbulence parameterization should work, even just the vertical. But the biology there is fairly straightforward to simulate. The other station is Bermuda. There is definitely horizontal advection, so vertical models do struggle there, but you can do okay, you can do well enough, but there's lots and lots of biological activity there, and it's been recorded for a number of years. The biological activity is very different between the 2 stations as well. So if you can simulate both of them with the same model, you're doing okay. And then finally, we've also looked at Station India. Again, lots of horizontal advection, so 1D model is not expected to perform very well, but again, very different biological characteristics to the other 2 stations. So the idea is that we use the same biological model, all 3 stations. We don't alter our fluxes in any way depending on where we are. So we can use this model globally, and it should give us a reasonable answer. So this is for fixed meshes at Station Papa. So the first, I'm going to show these kind of graphs a lot. So the green dots are observations. I've taken all observations I can find, plotted them as a year date, and then repeated them for however many number of years. which is why station path and mixed layer depth has lots and lots of dots, because there's 30, 40 years of observations all put onto 1 year and then repeated. And these are different resolutions in a fixed mesh, and the point of this slide is just to show that the mesh has a small difference on the mixed layer depth, but not a huge difference. You see most of them follow the observations quite nicely, and we do get some semblance of convergence in that is a 20-meter one, but the 2.5 and the 5 meter basically on top of each other. So the answer is kind of some semblance of convergence. And if you look at the surface chlorophyll, which is this next graph, basically it's flat throughout the year in the observations, and our model basically produces that nice flat line. We also look at the primary production. At station path, it's calculated as an integrated over the mixed layer depth primary production, and you basically should see 2 peaks. We don't quite get a second peak, but it's not too bad. And then the surface nutrients, again at station path, the data is quite spread out, but it should basically be a nice gentle wave with no real change over the year. And you can see we do a good job regardless of the resolution they use. We can move to Bermuda, again fixed mesh, and we do a pretty good job here. Very different mixed layer depth characteristics, but we do okay. And the surface chlorophyll again is very good. The primary production is this time averaged over the mixed layer depth, just for a bit of fun, I guess. But again, we do quite a good job of representing the data, even though we're in a regime where horizontal advection is important, and we're doing a 1D model only. And the surface nutrients is an important one at Bermuda because it's nutrient limited. So you should get 0 nutrients at the surface for large amounts of the year, which is what we do. Notice we're spiking a little bit here. That's due to the mixed layer depth deepening. Still within the data, but that results in little spikes in the nutrients. But this is fine. And the important feature at Bermuda that we should reproduce is this so-called subsurface chlorophyll maxima. So this is this balance between sunlight coming in and nutrients coming up, and most of the phytoplankton sit at depth between 50 and 100 meters. And at Station India, we do it again. The results are fine, good mixed layer depth. Surface chlorophyll, we spike a little bit too high, which spills over into the primary production, but the nutrient behavior is very good. So we are capturing the essential dynamics of these 1D systems using our model. So what about when you add adaptivity to this? So remember, we've got turbulence parameterization, nonlinear tightly coupled system. We've got this biology ecosystem model, a tightly coupled nonlinear system. And then we're going to stick adaptivity on top, which is another nonlinear effect. We can construct the metric by which we base the edge lengths using a number of methods. So for example, I could use the velocity and density to construct this and work out the curl of those. I could also use n squared, m squared, which is the buoyancy frequency, and the shear velocity, which are the source terms, into the turbulence parameterization. And I could just use the turbulence parameterizations itself. So basically, these are attempting to adapt the mesh to the parameterization, the physics that's going on. I could also adapt to the biology. So for example, I could do the naive thing and adapt to the photosynthetic radiation. You would expect the resolution to be concentrated at the surface, but not at depth. Kind of makes sense for everything's going on. And I can adapt to various combinations of them. So for example, I could adapt to the velocity field, the density field, and the detritus, which would then allow me to track the fall of detritus. So if you're interested in how the detritus hits the benthic fauna, then this could be a good metric for you to use. And because we're interested in nutrient fluxes, I've obviously also looked at adapting to the nutrients as well. So the first problem is that as soon as I switch on adaptivity, all the rest of the fields, mixed layer depth, the chlorophyll, the primary production, look fine. You can't really tell the difference. But we get this, you can see the red line is the fixed mesh simulation. And as soon as I add adaptivity, regardless of the metric, I get this drift in the surface nutrients. So we've somehow, by adding adaptivity, we've added a flux upwards of surface nutrients, of nutrients to the surface. It does depend a little bit. For example, if I adapt to this biophys is adapting to velocity, density, and nutrients, it's a little bit lower, which is good because we're adapting to nutrients. We would hope that would be the case. But even adapting just to radiation, which is really naive and probably a stupid thing to do, the drift is there, and it's not that much different. So one of the things that Matt mentioned in the first day was we can change how often we adapt. Now, unfortunately, I ran these runs and then we had a power cut on the supercomputer, so they didn't finish. I haven't got around to finish them off, but effectively, the previous one was using this kind of adaptive time step, which is every 20 time steps in the model. And as we decrease it by a factor of 10, so every 2 time steps, you see the nutrient drift kind of comes in. So it looks like every time we adapt, we're kind of adding a little bit of push, a bit of energy into the system and fluxing these nutrients up. But where's this energy coming from? What is the cause? Is it just literally interpolating between meshes, and is that adding diffusion? So to test that, I stripped out the physics. I pre-recorded the physics on a fixed mesh, and then just ran it with just biology. So I'm just looking therefore at the effect on biology, and regardless of the metric you use, you get a perfect answer. So it looks like the extra oomph in terms of bringing stuff to the surface is coming from the physics part of the simulation, despite the physics looking absolutely fine by themselves. Skip that one. This is what the meshes look like. So I've gone down a column and just put a black dot every time I see a vertex. So you can see, for example, the mesh is really nicely following the mixed layer depth, which is the red line, if we adapt to the buoyancy frequency. You can see you get some kind of cascading coming down, and you get some quite interesting meshes. The photosynthetic radiation mesh looks very boring, nothing much changes, basically because at 200 meters the sunlight is still there and there's nothing much happening. Down at depth, these elements get very large, but that should be fine. So really, I'm stumped at that point. I'm not really sure where this extra oomph is coming from and exactly how it's being caused. The physics look absolutely fine, and you only actually see this problem when you add biology. So yesterday, when we were discussing what kind of test cases to use, I would advocate having one with some biology in. Your physics may look fine, stick an ecosystem model on top, and suddenly everything looks not quite so fine. And we found this a lot while developing this. I would say, yes, my physics worked perfectly, and then Kachi would come back to me and say, nope, the biology is poking a hole in your physics. So that's my first conclusion. And I do have time to go for the restratification. So Matt showed this problem briefly on the first day. Flora McTavish, PhD student, did the setup. It's a cylindrical domain, 250 kilometers across, I think, with a cold water chimney in the center. That's a cross section through there. You can see the cold water chimney. So as you let this go, it should restratify, and you should get some nice eddies and effects going on around the surface. So unlike Levy's earlier attempts, this is a kind of dynamic system. Hers were kind of quasi-stable. This is very much a transient kind of system where we really should see a single bloom coming in. And I want to look at the effects of resolution. I look at the multiscale effects going on here. So the biology setup is initial conditions very similar. There's high nutrients where there's low temperature, and there's low phytoplankton where there's low temperature. The phytoplankton obviously just sit at the surface, and the nutrients go down to depth. So we should expect to see a nice big bloom over these high nutrients. And then I've run this at various resolutions and looked at the primary productivity. So we would expect, as I increase resolution, I resolve more sub-mesoscale processes, I therefore should get higher productivity. And the 20 kilometer one hasn't quite finished yet, but you see the productivity is there. The 10 kilometer is highest, but then as I increase resolution more, I actually get lower productivity again, which is slightly odd. If I look at how much nutrient makes it to the surface, the 20 kilometer, the low resolution run, has fewest nutrients to the surface. That makes perfect sense. I'm not fluxing things to the surface, and I'm still getting biological activity at the surface, so I'm using those nutrients up. So hence, the nutrients fall down quite quickly at the surface. And you can see they actually grow for the higher resolution runs as you're fluxing nutrients to the surface, and then they start to decrease. The really interesting thing that I'm now looking at is this divergence. So the 5 kilometer run seems to have settled at a state, or appears to be settling at a state around here, whereas the 10 kilometer run is still growing in nutrients. But the dynamics are just about finished by this point. So it's interesting as to why these the ecosystem model is settling into different states depending on spatial resolution. I've also done a 2.5 kilometer run for this as well, and you can see as you increase resolution even more, you get even more chlorophyll at the surface. So it's not a straightforward linear convergence type test where if you keep increasing resolution, you converge onto a solution. It doesn't seem to be doing that. And I have set up 1.25 kilometer resolution, and I suspect I will have to go even further, which I hope I have enough hectare AUs to do all these runs. So in future, I mean, the obvious things to look at is where is this extra flux coming from in adaptivity? Is it just the way that fluidity does adaptivity, or is it general to all adaptive methods? Is it just because I'm changing the mesh, or is it what is the source of this extra flux? And to carry on with this restratification problem in terms of extending it to different resolutions, do I eventually converge? So if I go to 200 meter over this 200 kilometer domain, will I actually get to the same answer as 400 meters? And then switch on adaptivity, and fingers crossed, you would hope that you can actually zoom in on the resolution and get a good answer that's very equivalent to the highest resolution run, but for far fewer nodes, and in which case that's a big plus for adaptivity. And I think a big selling point for us as a group in terms of this is the type of problem that we can use to sell adaptivity, because there's no way that you could run a global simulation at 200 meters resolution on a uniform mesh. And because these plankton blooms are ephemeral and you don't know where they're going to occur, you need adaptivity through the run rather than because you don't know a priori where they're going to occur. So I'll show the movie now because it looks pretty. Hope this works. This will be when the movie doesn't actually work in Windows or something. So this is the chlorophyll. So this is basically the plankton bloom at 5 kilometer resolution. You can see it's extremely brief, lasting a few days at most. But you can see that the fine filaments starting to develop and everything else. But this is just 5 kilometers. So I'm going to get really fine structures when I get down to 1.5 kilometers.
How long is the simulation?
The entire movie is 35 days. So that bloom is lasting a few days at most. And you might just be able to see the diurnal effect. It slightly pulses.
Rubbish visualization?
No. So I'm just going to summarize. I don't think I have any conclusions as such. Fluidity, we've added an ocean ecosystem model along with turbulence parameterizations and bulk formulae for the ocean, so we can now do reasonably realistic ocean simulations with those. Adaptivity and subgrid scale parameterizations do appear to work if you look at them, but then you add biology, which then points at the tiny holes in that. So any test cases we come up with, one of them should definitely have some kind of biology ecosystem model in it. And biological ecosystem models in the ocean respond to resolution, though it's not in a very, both temporal and spatial, but not in a very straightforward and obvious way. And I'm really interested in trying to figure out how we can quantify what kind of error we expect at a certain resolution in our model. And basically, I'm trying to couple highly nonlinear systems with adaptivity, and obviously I found this is non-trivial, which is not really a surprise, but there you go. Thank you.
There are two very distinct effects happening in the mixed layer, and which of them, you can get one of them if you resolve the baroclinic deformation radius, the first mode, the greater mode. The other, you need to resolve the deformation radius associated with the stratification of the mixed layer itself, which is tiny. The first effect is that you can have lateral stirring up and down along density surfaces,
Right. Okay.
but there's a gradient in nutrients because the biology strips it out. That's Marina Levy's thing.
Yeah.
The second one is that within the mixed layer, fronts restratify.
Yes.
And the typical length scale for actually resolving that is very small. It's based on just the stratification of the mixed layer itself. And you're looking at scales, I don't know what they would be in this case, but like of order kilometer or so.
Okay.
Bailey Fox Kemper has done some really nice studies of that. Two questions. One, have you looked at your resolution compared to the mixed layer deformation radius? And secondly, have you thought about using something like Baylor's parameterization of the restratification effects?
Okay, so the first one, for the restratification problem, there is no mixed layer in terms of there is no, so So the mixing is all dynamic, and there's no forcing on the surface. So right now, there's no a real need for a mixed layer at the top because there's no wind stresses, there's no heating at the surface. So
Stratification will happen.
the stratification happens, but there's no the GLS is not really functioning in the mixed layer at all. So I've turned it on, but it's not doing anything because there's nothing really forcing it. The stratification is fairly weak, and there's nothing much happening in terms of that density. So that first question, no, I've not got to that yet, but obviously when I start adding surface fluxes to the restratification problem, I'm definitely going to have to look at that kind of problem. And as for the other parameterization, no, I haven't considered looking at. But yeah, it's something definitely worth looking at in terms of that might explain some of these answers. Yeah.
So do you know what the sort of reaction order is that, on the reactions you're looking at?
I don't know. No.
If you could reduce the reaction order to like 0th order reactions or even 1st order reactions, then you could just have a system of 1st order ODEs, and then you could probably find an equilibrium solution to test to make sure that you're converging to the right.
Yeah, yeah. So, yeah.
I mean, I imagine it's probably fairly nonlinear the way that you're coding it.
It is.
now.
It's really nonlinear.
Yeah.
But yeah,
It's a second order nonlinear.
It is.
Well, it depends how you want to write your ODEs, but there are 4 variables in second order in those variables and highly nonlinear. It's a bit complicated because it's not second order in all the variables, Colin, but it's high single digit order and nonlinear. Whether or not it's straightforward to back out.
Yeah, but at one point he was just restricting to the kinetics part. He was getting this sort of dynamical, this oscillations period, and saying it wasn't converging to an equilibrium state or any sort of. Isn't that what you said? Maybe not.
No, when I stripped out the physics, I was just pointing out that I no longer saw the surface drift. So it's not adaptivity reacting with the biology.
Oh, yeah.
That's causing the surface drift. It must be somewhere in the parameterization, I'm guessing. But I obviously need to try and figure out where it's coming from.
I mean, as soon as you have dynamics on, the biology is never in an equilibrium state. That's kind of the problem, right? So
Yeah.
we can run, and we have run, the biology model offline, zero-dimensional at point in order to verify the implementation of the biology model. So that's done and that's tested, and we're pretty confident that the biology model is correct. That's kind of the easy bit. Biology models are not hard to write. They also famously aren't real good on skill, but what they are really, really good at is showing you where your dynamics are from. That's the...
Are they stochastic? The kinetics are using stochastic?
Do you have a biology test case where you think you know the right answer?
I don't think such a thing exists in terms of whenever there's real data, you've got sufficiently. I mean, I could come up with a theoretical problem, right? And I get the right answer for things like the 0th order convergence. I mean, it's fine. I'm sure that I'm very confident that the model is actually converging and working properly. But the problem comes as soon as you start doing something even slightly realistic. The data is sparse, there's huge errors, and it's really, really difficult to know if you are getting the right answer. The model skill in biological models is notoriously low, and in fact, if you make a more complicated biological model, add more, you would hope to get a better answer, but in fact, you don't improve at all. That's partially due to the sparsity of data that we have to compare against.
Conversely, you can fail, right? So it can be very difficult to write a biology test case where you know you've passed, but they have quite a lot of failure modes that are obvious. So a model can definitely definitively fail them. It's just very difficult to say that they've passed.
Yes.
So there is still useful information in there.
So the one difference, like we can see with the dynamical system, is that you have conservation loss. So you can make test cases. Whereas this is a phenomenon.
No, biology is conservative.
No, it's
Biological transfer is conservative.
they're conservative. Nothing is lost in the system. It might just sit as detritus at the bottom until it remineralizes.
But like we are looking at a regional
Well, only if they're elementary.
domain. Even that, does it hold?
Yeah, as long as your domain is conservative, you're not fluxing things out of the boundary, then yeah, it holds.
And you can measure the flux of the boundary, so you know what your
You know what? You can, and we have checked that everything's conservative. Even with adaptivity, we just run the biology model. You can add all the boxes together, and you are within times 10 to the minus 12 conservative. So, in this kind of sense, it's.
Right, so we're into the coffee break now, but before I let you go and recaffeinate, Hilary has an exciting announcement for us.
Thank you. I would like to. I've been talking to the editors of Geophysical Model Development.
Scientific model development.
Sorry. Geoscientific Model Development. And we'd like to have a special issue related to the whole programme. The nice thing about a special issue in GMD is that you can submit your paper whenever you like, and it will appear as soon as you submit it, rather than appearing when everybody submits their paper. The disadvantage of that is you don't have a deadline to submit your paper, so it may never happen. GMD hasn't traditionally published a lot of papers in numerical analysis, but if we all point to our browsers at GMD and get alerts relating to numerical analysis, then that will change, and we'll see each other's papers as they come out. So please have a look at the table of get a table of contents alert for GMD and submit a paper to the special issue. Thanks.
Years.